Okay. Yeah, thanks, Keith. Yes, as you mentioned, my name's James Davidson, Senior Cable Consultant with OWC. My background is in offshore cable construction. After roughly 8 years on the continent and on various projects in the EU and the UK, mainly on offshore wind farms, but also scattered experience on interconnectors and other scopes. Quick summary for today. We'll provide a very brief introduction for OWC, and we'll go through some submarine cables technology introductions. I will go through some principles of fixed bottom and floating cable lay, and then talk a bit about the evolution of cable lay vessels for the fixed bottom market and what this might mean for the floating market going forward. At the end, there'll be a Q&A. Well, so I would like to address questions on the spot. Please keep them for the end so that we can ensure that everyone, both those in the room and those online, can be involved. AVL Group, we think of ourselves as a global partner and a local expert. We have offices all over the world, from the US, UK, EU, and all the way down through APAC to Australia. AVL is a relatively large independent energy and marine consultancy with OWC and associated affiliates, NOC, East Point Geo, and Longitude, providing the backbone of our engineering capability in the cable space. For OWC, OWC itself has a long-standing experience of developing and realising offshore projects. We are the offshore wind consultants, although we found that the market demands and we can support across the renewable space, providing services across offshore winds and onshore wind, solar, and other renewable projects. It was established in 2011 by a small team of experts who have been involved in offshore wind farm construction since the 1990s. We are a global specialist in offshore wind with a low bid, but we do try to maintain a local presence. We have approximately 100 people working for OWC across 11 countries, with dedicated teams in London, Edinburgh, Cork, Hamburg, Warsaw, Taipei, Tokyo, Vietnam, Busan, Seoul, Boston, New York, and Rio. We've also been largely active in the floating wind space since 2017, with work across early stage projects like Kinkini and Erebus. Submarine cables. This talk is intended to be quite broad, so we don't want to assume everyone here is a cable installation expert. As such, sorry, one second. Okay, so submarine cables for offshore wind farms, there's both static and dynamic cables. The market at the moment, or the mature part of the market at the moment, is all static fixed bottom installations, where we have offshore wind arrays connected to offshore substations with inter-array cables, and then the power is exported to shore via export cables. Both the wind turbines and the offshore platforms themselves are all fixed bottom, either on monopiles with jackets. These fixed bottom installations, the sort of water depths that these can be installed at, kind of max out at about 100 meters. Shallower waters are suitable for monopiles, and then jackets of structures can sustain turbines and offshore substations up to water depths. Well, around 100 meters is the current threshold. Beyond that, you're looking at floating structures. We're not going to go through all of them in detail, but these go through a whole gamut of concepts and designs, from tension leg platforms, semi-subs, barge designs, and floating spars. All of these structures kind of have the same sort of components. There is a foundation or a hull. There's a transition piece, which doubles as an access platform. There's a turbine support tower, and then the nacelle and the blades on top. Of course, all these structures are connected to each other with submarine cables, and floating structures have the requirement to be tethered or moored to the seabed via various methods. Submarine cables. Typically, submarine cables are three-phase cables. or three AC cables with three cores. These cores can be copper or aluminium. They're protected by various layers of insulation and protection. There's other components such as screening and fiber optics components in there as well. And there's also armor layers to protect the cables during installation and burial, and outer sheathing. Where there is differences between the static power cable and the dynamic power cable market is mostly in the outer protections. Because of the more strenuous conditions that they must be installed in, dynamic power cables are often double armored and have more robust sheathing. And this, of course, adds significant weight to these products compared to conventional static power cables. There is also quite different handling requirements for these products. Static power cables may be coilable, which means they can be stored in non-rotating or static tanks, whereas dynamic power cables, they do require different handling and need to be stored appropriately, either on reels or in rotating turntables. Dynamic power cables are also typically harder to handle. They have greater stiffness, as I said before, greater weight, and are overall more robust products because they're designed for a totally different regime. It's probably worth noting that while static power cables are, we are pushing the boundaries of what they can output. Conventional standard technology is around 220 kilovolts. But projects going forward into the future, they are looking at 275 and above for export capacity. Dynamic cables, whilst they're pretty similar to cables used for umbilicals in the oil and gas market, these products currently max out at about 115 kilovolts, and this is a constantly developing space. And the capacity to power offshore wind farms at scale is still in development, both in the terms of product development, but also in the standards that these products need to be developed in accordance with type testing and specifications and that kind of thing. Components of a typical dynamic cable arrangement. On the screen, on the graphic on the left, you can see a floating spar turbine with three moorings. The cables will be connected into the turbine in a configuration of the gain, of which there are many. This one on the screen is one of the most common ones, which is a lazy S. The elements that you can see are the cables themselves, buoyancy modules, bend stiffeners, cable protection systems, and potentially joints where dynamic cables may be connected to static cables for transmission to shore, or if there's a long length of cable on the seabed that needs to be buried. One thing that also sets apart dynamic cables or umbilicals from static cables is the type of termination. These terminations are quite heavy. They're quite significant structures. They can sometimes weigh hundreds of kilograms, and they're this way because they must be designed to sustain dynamic loads in a range of configurations. And it's also worth noting that one of the potential advantages of floating offshore wind turbines is the ability to totally disconnect them from anything connecting them to the seabed, such as mooring lines or cables, and tow them to shore for maintenance, for serious maintenance and repairs. A typical cable termination might take a couple of weeks to complete in the fixed bottom markets, which is why significant effort is being put into this problem by developers to develop wet and dry quick make connectors, which can be quickly removed from the structure and reconnected, of course, once the turbine is ready to be put back into operation. These terminations can be installed either in the factory or at sea, and depending on which choice you make, it greatly impacts the storage options for these products, which is a significant constraint going forward, and something that needs to be carefully considered in your logistics strategy for these projects. The question that maybe wasn't answered is why actually look at floating offshore wind at all. The reason is that it's a commercial maturity. With 4 gigawatts probably installed by 2030, some of the benefits of offshore wind, floating offshore wind in particular over static wind, is that it can bring offshore wind to new markets who currently don't have access to suitable seabeds or fixed bottom wind. It can increase offshore wind capacity for existing markets with competition constraints on the existing seabed, like fisheries, conservation concerns, or tourism. It can reduce emissions from offshore oil and gas production by exporting power directly to offshore platforms, and provide local economic benefits, as floating wind turbines may be more reliant on access to local ports and infrastructure. Now, some of the larger projects that are currently in operation and under construction are High Wind in Scotland, Kincardine, Windfloat in Atlantic in Portugal, although much larger projects are on the horizon. Okay, back on track. Cable laying terminology. Offshore cable installation is a complex task. In the planning phase, an installation analysis is normally performed, which considers factors such as cable properties, route characteristics, available installation equipment, and capacities of the cable installer. Just some very basic terminology here. You have a cable lay vessel, you have a cable, which has a cable weight. The catenary is the point between the touchdown point and the cable lay vessel chutes. Some key parameters are departure angle, top tension of the cable, the bottom tension of the cable, and the layback. The catenary must be managed at all times in order to preserve the integrity of the cable, and these specifications are provided by the manufacturer for the various products. At the foundations, the cables are installed by first and second end pull-ins. For static applications, these cables are fixed. They are often stabilized with cable protection systems and maybe rock berms on top to ensure that they do not move, because these systems are largely not designed to cope with dynamic loads, something which dynamic cables must, of course, consider in some detail. For dynamic cables, it's a bit different. We saw the lazy wave earlier. For this, the cable is installed towards the floating foundation by the cable lay vessel. The cable is then essentially entirely overboarded. Buoyancy modules are installed. Transfer is made between the vessel and the floater, and the cable is pulled into the floater using a winch on the floater, with the catenary kept in place by various buoyancy and maybe tethers on the seabed. This buoyant section is required in order to increase the length of the catenary, because floating wind turbines, they move. Thus, these systems must be designed to accommodate a wide range of positions, and they do that by the means of this buoyant section in the middle, and they can also have a tether on the seabed in order to restrain the touchdown point due to environmental loading. What this means, of course, is that these buoyancy modules, well, there's quite a significant number of them per cable, which will become relevant later on. This is an illustration of the fact that these floating offshore wind turbines move, and thus these cable catenaries must be designed to accommodate a wide range of motions. It's not just the motions, it's the fact that over time, these catenaries will accrue marine growth, and also the properties of the buoyancy modules and the cables themselves will change, which will again encourage the catenaries to respond differently to environmental loading. Thus, there might be a big difference between the installed configuration of a dynamic cable and the configuration's end of life due to marine growth and other factors such as compression and water absorption by the materials. Evolution of cable lay vessels. Silver utilization. Based on a study done by Blix in 2022, there is currently approximately 32 dedicated cable lay vessels on the market. And at the time, this was not anticipated to increase in any significant way, although since then I think there are 1 or 2 new builds announced by the likes of Prismium and various others. The length of a new build, well, it takes about 2 to 3 years lead time to build a dedicated cable lay vessel. However, based on these numbers, and I know there's been some sort of uncertainties in the market and projects being delayed lately, but it does show a structural discrepancy between the demand and the availability of cable lay vessels going forward. And this is pretty much just for fixed bottom wind. let alone the new capacity required by floating offshore wind. It did show a couple of graphics that showed the structural discrepancy in the amount of cable lay vessels available versus the projected growth of the market. So at the moment, I think there is a discrepancy between maybe 10 to 20 vessels, and that is a wide range, and it could, of course, be impacted by the actual pipeline of wind farms going forward. But the structural discrepancy is there. Basic cable lay equipment. All cable lay vessels have some similar attributes, although there is a wide variety of types and of vessels for different jobs. But they all have a cable storage tank. They have a deck tensioner to manage tension. They have a crane to assist with installation of cable protection systems and cable handling. They have a chute and cable highways for deployment of the cables themselves. All this equipment must be mounted on a vessel with suitable positioning capabilities. Whether that's an anchor spread or a DP2 is very much dependent on the job these vessels need to do in the field. I see that there is some strange things going on with the formatting, but okay, vessels fall into some archetypes. Again, there is a lot of cross capability and vessels which try to fulfill different functions. But broadly, there are vessels for shallow works, and these are barges with anchor spreads or maybe anchor spreads plus DP2. They also have the most variety in cable burial equipment because these vessels are often forced to operate in areas where there's high vessel traffic, which often complicates burial requirements requiring deeper burial and burial in more challenging conditions. The next group of vessels will be those dedicated to the installation of inter-array cables. These vessels have developed to have cable handling equipment that is very specialized for repeated operations, because these vessels specialize in installing a lot of cables over a very short period of time. So they have turntable capacities that are on the slightly lower side. They have more deck handling equipment to handle the vast numbers of cable protection systems, and just everything is sort of tailored to increase the repeatability and predictability of operations. And these vessels at their peak, they can install something like 2 to 3 cables per day, but some developers think that they could push that to 4, which is, really pushing the envelope of what is possible. The last classification of vessels are those dedicated to interconnectors or export cable lay. These ones have very large turntables, 5,000 and 7,000 tons each. Maybe they have 2 of them, either stacked on top of each other or in parallel configuration. And these are for larger products, maybe DC cables, servicing the interconnector and export cable markets. They're usually DP2, but they are capable of maintaining higher top tensions with bigger equipment. And they also have simultaneous lay and burial capabilities where they can lay cables and bury them at the same time. They can also bundle cables, which is particularly relevant for the DC market because they have multiple turntables and multiple firing lines to allow for these activities. Again, there's a lot of cross-roll vessels. Every contractor, they want to maximize what their vessels can do. So typically vessels might be designed to accomplish 2 or 3 of these tasks, or 1 to 2 of these tasks. Some examples below is a vessel called the Boca Spirit, formerly the Stammet Spirit. It's an old workhorse of the industry, and its speciality is shallow draft with beaching capability, so it can actually beach fully on dry seabed for very specific projects. She has an anchor spread and DP2. She has deck space for cable protection system containers, and she also can fit a jointing, she also can operate in a jointing configuration and take a plow on board as well. This vessel is a flat bottom vessel, and as such cannot operate in the highest workabilities, but if you talk to the crew, they are convinced it can work anywhere, anytime, in any conditions. The Livingstone is another such vessel that is trying to fulfill multiple roles. She has 2 5,000-ton turntables, which would indicate that she's for the interconnector and export cable markets. But she also has a very complicated cable handling system developed by Mutz, I think. They call it the cable installation system, and it is very much tailored towards repeatable handling of CPS. I don't know if you can see on the screen, but there is space there for, I think it's 4 or 8 stacked 40-foot containers full of pre-assembled cable protection systems, which can be pulled around this cable installation system, specifically for array projects. So whilst there are 3 main vessel archetypes, contractors try to maximize the capabilities wherever they can, and they come up with some pretty wild ideas. Okay, so the issue with all of these vessels for the static lay market is that the top tensions that they're designed to cope with is for a set water depth and a specific classification of products. These water depths, as you know, again, they're probably around 100 meters of water, products that are about 100 kilograms per meter, which means that deck equipment is typically sized at around 15 to 25 tons holding capacity to manage these catenaries. In order to move further offshore and into floating wind applications, these forces will increase dramatically. And the challenge for the cable lay fleet in the fixed bottom market is how do we increase capacity of these vessels without making radical changes to their equipment and deck spreads. These tensions increase for a couple of reasons. The first is, of course, related to the method of cable deployments. There's 2 main ways of cable deployments. There is a horizontal lay, which causes an S configuration, and there's a vertical lay configuration called, most commonly known as J lay. The differences between S-lay and J-lay become apparent when you look at where the tension is applied to the cable in the system. For S-lay, you have cable bends under tension because the tensioner is behind the cable before the bends, whereas for J-lay, the cable is deployed in a straight line with the tensioner in line with the cable catenary configuration. The layback must always be managed to maintain the cable within its properties. For that reason, S-lay, you will need to exert some additional tension in order to maintain this shape. The second main reason for the increased tensions for horizontal lay systems or S-lay configurations is the capstan effect, where friction of the cable over a static chute that will increase the required tension to hold the cable in position. Particularly when trying to recover the cable over a static stern chute. The capstan effect essentially is that when you apply a load around a bend, you require more holding force in order to break the friction effect and recover cable. How can CLVs accommodate higher top tensions? As we said before, typical deck tensions are around 15 to 20 ton capacities. There are a variety of ways that vessels can increase these tensions, and that is mainly due to alternate equipment. If you look at a vessel like the Nexans Aurora, they will use they use a piece of equipment called a capstan, which I think has 100-ton pulling capacity. In this case, instead of passing the cable through a linear cable engine, you can wrap the cable around the capstan in order to achieve markedly higher holding capacities. In order to reduce the capstan effect, you can replace the static chute with wheels, and this will, instead of sliding the cable over the chute, the wheel will rotate, and that will of course reduce the friction of the cable. And the third way is to just simply upsize the tensioners. You can replace these 15 to 20 ton capacity tensioners with larger tensioners. Tensioners, they go all the way up to 100 plus tension, 100 plus tons of tension capacity. But in order to do that, you also need to increase the capacity and modify your deck arrangements such that the whole system can take these loads. So how can we so why are traditional CLVs potentially not suitable for larger dynamic cables and umbilicals? Well, again, is because of the higher product handling requirements of umbilical products. It's the reliance on horizontal lay systems. It's the difficulty of making the required modifications and installing additional deck equipment. And it's the fact that these vessels are often, well, they're going to be utilised in the fixed bottom market. So if we do need a whole bunch of additional vessels, it's not clear where they're going to come from unless it's from the oil and gas market. So a bit of a case study, probably the most, the best analogy to a floating offshore wind project will be the installation of an umbilical for a floating oil and gas structure. So there was a project in the Goa oil field off the coast of Norway. It is a 98-kilometre route to an oil and gas platform. The cable system is a 115 kilovolt static cable with 240 millimetre conductors that is jointed to a 115 kilovolt dynamic cable with 300 millimetre square conductors. Please bear in mind this is still small, it's quite low capacity compared to what is necessary for exporting power from wind farms at scale, which is 220, 300 kilovolts. The installation was done at the N102, which is a McDermott in water depth up to 540 meters. The project involved the shore landing of the cable, laying of the cable, including down steep underwater cliffs, safe handling and overboarding of the bend stiffener and pre-installed hang-off termination, and the installation of the lazy wave, which had 73 permanent buoyancy modules. The way this was done, it was the vessel was fitted out with 220-ton tensioners in series in a horizontal lay configuration. They also used a motion heave compensated chute in order to increase the workabilities for the expected conditions. You can see here on the bottom left, the two tensioners installed in series, and on the top right, there is the umbilical being pulled into the platform, the winch on the platform, and you can see the bend restrictors and the termination there. The N102 these days is a specialised vessel for the flexible product installation market, and instead of having these two tensioners in series, it's now fitted out with a full vertical lay system, or a J-lay tower. And she also has this a carousel with a top hat, which allows for the storage of these pre-installed terminations. So the M102 is quite a capable vessel, especially for these sorts of umbilical installation projects. And it has some characteristics which are very different from most of the CLVs currently servicing the static offshore wind markets. Sorry guys, I appear to have loaded up the wrong presentation again. Sorry. Go to my team's name. Yeah, it's the wrong one. I'm going to share this one. Am I currently sharing it? It's all right now. Sorry. Okay, the N102. Yeah, so the N102 should be thought of as the model for what is required to install dynamic cables in deep waters because of the various characteristics that has been fitted out with, including the high-capacity turntable with the top hats, the vertical lay system with a 300-ton tensioner, and other useful items, 250-ton main crane, DP2 capability, and it can handle products from 50 millimeters to 620 millimeters. Okay, Okay, so what do vessels need for installation of dynamic cables? They need the capability for handling larger and heavier products, including pre-installed terminations. They need to manage high top tensions due to deeper waters and longer catenaries. They need good station keeping and workabilities for operating in difficult conditions in close proximity to the floating turbines. And they need, and this is probably the most important thing, is they need high storage capacity for dynamic products and accessories.
Sorry, go back to your slide.
This one, okay. Apologies for all those online, but this is really the crux of the issue, is what do vessels need for the installation of dynamic cables? And again, they need the capability for handling larger and heavier products, including the pre-installed terminations. They need to be able to accommodate high top tensions due to deeper waters and longer catenaries. They need good station keeping and workabilities for operating in difficult conditions in close proximity to floaters. And in all honesty, that kind of eliminates a lot of the fleet, the flat bottom fleets, such as the Stammet Spirits or the Boca Spirits and other similar vessels. They definitely need high storage capacity for dynamic products and accessories, such as these buoyancy modules on the side. That cable on the Goa project, it needed 73 individual buoyancy modules for one product. If you're going to extend installation capacity to multiple products in the tens or around to match the number of turbines in floating offshore wind projects, the storage of these sorts of accessories is going to be a key issue. Another vessel on the market that sort of fits this profile is a Norman Clipper from Global Marine. She has a vertical lay tower, plenty of deck space, and a turntable for storage of flexible products. The other key issue is, how do you store the products? There's various ways to do this. You can either store them in turntables or on reels. The benefit of reels is that you can easily have pre-terminated cable ends. The number of reels that you need is proportional to the number of products you need to install. You can maybe install a couple of products per reel, but the most efficient way to do it is in a turntable. If you have your products in one continuous length, it means that you are going to be installing your terminations offshore, which greatly increases the duration of your operations and makes you more sensitive to weather windows and just impact of the weather. A smart solution is to have a turntable with a top hat or a bobbin. This is the one from the N102. And as you can see, there are various end terminations stored on the top with the cables coiled in the tank below. What we want to avoid in the floating offshore wind market is reliance on vessels such as the one below, which is the Constellation. This might be the most expensive vessel in the universe, and it's specialized for very specific deep water oil and gas projects with its vertical lay system and dedicated wheel drive systems. The other option is to look at the offshore service vessel market. These are not dedicated cable lay vessels, but they do have key things like the DP2 capability, suitable cranes, and sufficient deck space for the mobilization of modular cable lay spreads, as well as the ability to store the various accessories, such as the buoyancy modules. There are companies that are creating these sort of modular spreads, including MDL. The one shown here on the right is a nice little unit. It's a tensioner coupled with a wheel. So this does indeed reduce the capstan effect while giving a solution that can be easily mobilized to a broad variety of DP2 vessels, which could then be mobilized for the floating offshore wind project. It's also worth noting that whilst flexible umbilical products have similar characteristics to power cables, building institutional knowledge on the behavior of these products across a market such as the cruise for these sorts of offshore service vessels, that will take time. In conclusion, floating offshore wind is an exciting new technology, bringing opportunities to develop the resources in previously unreachable waters. This is an essential part of the future energy mix, considering climate and emissions targets. Installation will be required in challenging environments, requiring expertise and equipment sourced from multiple industries and offshore sectors. Floating offshore wind installations will encompass a wide range of water depths and site conditions, giving the opportunity to utilize assets servicing the current fixed bottom offshore wind market, as well as needing to rely on the offshore oil and gas market, where there is specific knowledge and equipment for these conditions. That said, in the oil and gas markets, these projects are often a one-off or two-off event with significant investment required for each product installation, whereas floating offshore winds will need to be done at scale. And as such, significant progress needs to be made on optimizing CLV configurations and the logistics chain to provide solutions for installation of dynamic cables in deeper waters. Offshore wind is becoming a global market requiring maturity of the supply chain, including associated logistics such as mobilization and load-out ports. As I said before, floating offshore wind turbines, they are much more reliant on local ports due to the assembly and preparation requirements. These cannot easily be transported from ports far away from the installation location, and they must be assembled nearby, bringing local jobs.